Hi, OWON sent in this CM2100B 20,000 counts AC/DC clamp meter for me to do a review on. This is a relatively new product, according to OWON, so of course I'm interested in finding out how well it works. And of course, we will do a teardown towards the second half of the video. Off the bat, it has some rather impressive specifications. It's a 20,000 counts clamp meter. The CM2100B version we have here, which supports Bluetooth, is for sale at just around $50. And if you don't need Bluetooth, you can get the CM2100 version without the B for just around $40. At this price point, I don't think you can find many competitors that supports this level of precision. Most clamp meters are 6,000 counts or less, and this is true for even more expensive ones. Now, this clamp meter is designed mainly for electronics and low power electrical systems, as the maximum current it can measure is at 100 amps. But this current measurement range is probably most people following this channel would be interested in. Here I have the HT20AD clamp meter on the side for comparison, and you can appreciate just how much more compact the CM2100 is. Of course, this is not an apple-to-apple comparison, as the 20AD can measure up to 1000 amps. The CM2100B is powered by two AAA batteries. I've already put them in, and we will take a look at the current consumption before the teardown later. The meter came with a soft instrument pouch. Inside you will find a user manual, along with a pair of leads and a screwdriver that is for the battery cover, so you don't have to hunt for a screwdriver when putting in new batteries. If you look at the back of the meter, you can see that we have this mounting point right here that is presumably designed for a wrist strap. But interestingly, the meter doesn't come with one. And the case itself, you can see that is rubberized, which makes it very easy to hold securely. The range switch feels pretty precise. It's a little bit on the stiff side, but with a rubberized wheel, you shouldn't have any issue selecting the correct range. One nice touch is that you can see we have essentially two of these off positions. One is on the top, the other one is at the bottom. The longevity of the range switch remains to be seen, and I definitely will report back if there's any issue over the long term. Now, I've had issues with range switches on clamp meters in the past. Given the harsher conditions these meters are typically used under, the long-term reliability of the range switch is something I think is going to be very important. Anyway, let's put in the stock leads and do some measurements. So let's plug in. And by the way, it would be better if the supplied leads come with straight banana plugs instead of these angled ones like what we have here, since the sockets are on the side. But that would be icing on the cake, and it's just too much to ask for a device in this price range. And by the way, the meter itself is Cat 3 rated. As you can see, it is printed at the bottom. Of course, we will take that with a grain of salt, as these kind of cheap meters usually don't have independent rating. Anyway, because it's Cat 3 rated, and the probes themselves are also Cat 3 rated as well, as you can see, we have these shrouds on top. And for our testing, we don't need this. We'll just take them off. First, let's test out the DC measurement. And because it's a 20,000 counts meter, you can see that we have a resolution of 10 microvolts, and that is quite impressive. The accuracy is specified at 0.5 to 0.7%, depending on the measurement range. And I have hooked it up to my EDC216A DC voltage standard, and let's see how accurate this meter is. Now we do have a little bit of offset. That's from the EDC voltage standard, not from the meter itself, as if I just disconnect the probe, you will see that the reading is essentially 0. Anyway, let me put it back on. And let me just zero it out first. So now let me increase the voltage 10 microvolts at a time to see if we can register that least significant digit here. That's 10 microvolts, 20, 30, 40, 50, 60. As you can see, it's very sensitive, but nevertheless, we are able to detect an increment of 10 microvolts at a time. 70. So no problem at all. And let's do 10 at a time. 10, 20, 30, and 1 millivolt. And that's pretty good. Let me tilt it a little bit so we don't get as much glare. All right, now let me do 1 millivolt at a time. 1, 2, 3. That is pretty accurate. I think we can jump straight ahead to 1 volt at a time. And for that, I think I need to take out the relative measurement here. And this is 1 volt. You can see the measurement is a little bit out, but I think it's still within the specified accuracy here. So let's do 2 volts, 3, 10, and no problem at all. Now let's take a look at the DC measurement speed side by side with my Unity UT61E Plus. For that, I have hooked both of these meters up with my variable bench power supply. So let me start ramping up the voltage. And you can see that the update rate is pretty fast on the CM2100. It's just the range switching is not as fast as the Unity UT61E Plus. I will do that again. You can see if I adjust output voltage really quick, you are not going to be able to see that voltage until the voltage stabilizes. But if I just ramp it down or ramp it up slowly, you will see that we are catching that reading with no problem at all. So the range switching definitely can be faster, but nevertheless is quite acceptable. Now let's take a look at the AC voltage measurement. For that, I have hooked both of these meters up to my Variac, and let me change it to measure AC. Now let me ramp up the output voltage. And you can see the readings, they do agree with each other. And the update rate is relatively fast as well, so that's not an issue at all. So it seems that on the AC side, the ranging is ever so slightly faster than the DC side. And the update rate is about 2 to 3 times per second, which is definitely good enough. Let's skip the current and non-contact voltage measurement for now. We will do that measurement later, but for now let's take a look at the resistance, capacitance, and ohm measurement range. Now the resistance range on this CM2100 can measure up to 200 megaohms. That's quite impressive. Of course, I don't have any resistors of that high value, but let's just gently touch the tips and see what we got here. You can see that we definitely are able to measure very high resistance here. Anyway, let me short these leads out. Seems the auto ranging is on the slower side, unfortunately. You can see that it does take about a few seconds for it to auto range. Now, that is actually quite typical, so let me first zero it out. The first resistor we're going to measure is this 100 ohm 0.1% tolerance resistor. So let's take a look. Since we don't have gold-plated leads, sometimes the lead resistance is going to come into play. So let's just adjust this. And you can see that we're actually pretty much bang on. And that's definitely within the 0.1% tolerance. And next, let's take a look at this 4.7 kilo ohm resistor. And I do need to take out that rail because that's only meant for very small resistance measurement. Let's take a look. It's actually not that bad. It only took about a second and a half for the reading to stabilize. Now let's take a look at the capacitance measurement mode. And the first capacitor we're going to measure is a 22 picofarad capacitor. Of course, we already have roughly 29 picofarad reading, so let's zero that out. And let's just take a quick look here. And you can see that we really have no issues at all, except the readings are not that accurate because we have these two very long leads. Now, if we really want to do it very accurately, we have to get the leads into position first and route it out. So for example, right now, let's try route it out. And now let's do the measurement again. You'll see now we're in the ballpark of that 22 picofarads capacitor. Now let's just skip to a large capacitor here. So this one is a 15,000 microfarads capacitor. So let's take a look. Now I got a feeling it's going to be very slow, but let's take a look at how slow that is. So as expected, you can see that we eventually get the measurement, and that took about 6 seconds. And the measurement is roughly in the ballpark of what is specified. So that is no issue at all. And now let's take a look at the diode mode. So the first diode is a red LED. And let's take a look to see if we can light it up. And you can see we are able to light it up. The forward voltage drop is 1.6 volts. Alright, so now let's take a look at a white LED here. And we are able to light it up, but we can't measure the forward voltage drop. Now, that is actually quite common for most multimeters. Now let's take a look at continuity. As you can hear, the measurement is definitely latched. Now, it is latched for a little bit too long for rapid changes, but that should not be an issue in real-world testing scenarios. Now let's take a look at the frequency measurement. Now, the spec didn't really say what's the maximum frequency it can measure. It did mention, however, the minimum waveform voltage needs to be greater than 1 volt. So let's put in a 5 volts signal here. So let me just get it set up here. And currently I'm outputting a 100 Hz signal from my UTG 962E. And the voltage is set to be 5 volts peak to peak. You can see we measure that frequency with no problem here. Now let me increase the frequency here to 1 kilohertz. And you can see we also have no issue. So let me go to 10 kilohertz. No problem. Now let's go to 100 kilohertz. How about 1 megahertz? Yep, no problem at all. So let's go to 10 megahertz. No issues either. Let me keep increasing. 20. Nope. Not able to do 20. Let's see, 11. Yep. 12. Nope. So it seems that for an amplitude of 5 volts peak to peak, we are able to measure just about 10 megahertz. And by the way, we also have a backlight here, so you can enable that by press and hold this button here. You'll see the backlight came on. Now, it is not super bright, but it will definitely be able to see if you're in the total dark. And of course, you can also hold the readings, and that's by a short press of the button. Alright, now let's do some current measurement, and that's your typical main use of a current clamp. And this current meter can do both AC and DC current measurement. We're going to start with DC current measurement. In my opinion, the 2 amp range is probably the best feature of the CM2100. Using this range, you have a current resolution of 1 milliamp, which is good for low current measurement. So of course, just like any current clamp meter, we have to zero it out. And the device here is you try to put it into position before you zero it out, as when you move it, the residual reading will change. So let's zero it out and put on the current clamp here. The UT61E Plus is measuring the same current here. So let me adjust the output current and let's see how well these 2 meters agree with each other. And we're at 1 amp. And the update rate of this CM2100 is actually pretty fast. So right now we're at roughly 2 amps. These two readings are essentially bang on. And let me adjust to the 20 amp range. And of course, the reading now is off, so let's readjust it. And you can see we have this residual. So zero it out. 2 amps. Let's do 3 amps. 4 amps. No issues. 5. And I think the maximum I can get is around 6 amps. And just for completeness, let's take a look at the AC current measurement as well. For that, I'm comparing the current reading to that measured by the HT208D. And for the load, I'm just going to use a DC power supply. I'm going to short output and adjust the output current. Currently, the power adapter is turned off. So let me change it to AC mode. And I'm going to change this one to AC as well. Let me turn on the power strip. And let me ramp up the output current. And again, this is just for you to get a visual of the two meters here. And we're roughly measuring the same current here. You can see that there is a little bit of discrepancy, but not by much. So basically, this gives you an idea of the AC current measurement. And you can see the update rate is pretty fast. The CM2100B also has a non-contact voltage detection mode. Now let's give it a go. And you can see we are able to detect mains voltage here, but it's not very sensitive. We have to get right close to the live wire here for it to start beeping. And this is unlike some of the other meters we have reviewed, where it's overly sensitive. You literally just wave your arm and it will go off. So it's interesting to see that. I'm wondering if the meter was designed and calibrated specifically for the 220 and 240 mains voltage markets. In North America, the voltage here is 120, so that could have explained the sensitivity issue. Now, this is just something for you to keep in mind. As mentioned earlier, the CM2100B version supports Bluetooth. With the phone application, you can actually do data logging with this meter. So let's take a look. And here on the phone, I have installed the iMeter application. Let me launch it. And to enable Bluetooth, all you do is press and hold this 0 button. You will see we have this icon flashing that's Bluetooth enabled. So let me go back to the phone. Now let me add a device. And by the way, the BDM, that's essentially the CM2100B. So let me select that one. And now it's connected with the phone. You can see that the reading is essentially in sync with what is shown on the device. Of course, I can change the range here, and the phone display will change accordingly. So if I change it to volts, you can see that we're displaying volts here. So let me change it to 20 amps, and let's hook up the power supply. Let's adjust the output current, and we'll see what we get here. You can see that the readings are essentially in sync with what is shown on the meter itself. Now, of course, we can do a lot more than just showing the actual reading. We can come to the chart here. You can see that we can actually plot the current versus time or whatever against the time. So if you are in the current mode, that's what we're currently in. That's the plot here. So let me zoom it in a little bit. And let's change the current output. And you can see that we get a nice plot. So this will definitely come in handy if you need to record some of the data points. So the data logging capability is definitely very useful and can come in handy. The application itself is fairly rudimentary, but it works quite well. I actually prefer this kind of simple applications that get the job done than those have a lot of bells and whistles that you might never use. Before I do the teardown, I do want to take a look at the power consumption of this meter. So let me remove the batteries here. By the way, as mentioned earlier, this meter uses two AAA batteries. Let's take a look. I really like this captive screw here, so you don't end up losing it. That's definitely a nice touch. And here are our two AAA batteries. So to do the test, let me hook up a multimeter. All right, let me turn it on. Wow. Looks like in steady state we're only drawing less than 1 milliamp. That's actually quite impressive. Let's see other ranges. 1.4 milliamps. 1.5 milliamps. How about current measurement? That draws about 9 milliamps. That makes sense as we do have a current sensor up here, so that needs to be powered. And I would expect the other current ranges are also around 10 milliamps. Yep. How about a volt measurement? Again, it drops down to 1.3 milliamps. So let's see if we enable the Bluetooth, what the current draw is. So the Bluetooth actually only adds about 1 milliamp, which is not much at all. So let's take a look at the current here. Yep, from 9 point something to 10 point something. So that's definitely very small increase. You can see that the CM2100B is very energy efficient. You can expect the two batteries to last a very long time. And if you are not doing current measurement, if you're doing voltage measurement, you can expect the battery to last even longer, as we're only drawing about a few milliamps here. Let's take a look at the backlight here. Alright, so it seems that the backlight only consumes 2 more milliamps, not a big deal. So that's actually very good. Now I have opened up the case. You can see the layout inside is quite compact. Here we have a off-the-shelf TLSR8261 Bluetooth module that handles the Bluetooth communication. I'm assuming the header footprint down here is for programming or testing the Bluetooth module. Towards the input side, you can see we have a single PTC for some limited protection. But there are no MOVs around by what I can see here. And that's similar to a lot of the other cheap multimeters I have reviewed before. So although the meter itself is rated for Cat 3, it's probably best to stay away from high energy circuitry when the leads are plugged in. There's no marking on the main DMM chip, unfortunately. I'm wondering if it's the same chip used in other 20,000 counts OWON meters, like the chips used in the HDS200 handheld series. To the left, we have two of these op-amps. These are SGM8956 precision rail-to-rail op-amps, and those are probably used in conjunction of the clamp sensor to amplify the current signal. Of course, because this meter also can measure DC current, there has to be a Hall effect sensor somewhere integrated inside the jaw here. Now, I do see quite a few of these trim pots here. Presumably, they are used to calibrate the current measurements. The larger pads in the middle here are for power input. The battery terminals on the other side are essentially just pressed on to these pads. This is a really nice design. Personally, I really like this CM2100B clamp meter. Considering this is a 20,000 counts meter that supports both AC and DC current measurements, and it has added data log capability via Bluetooth, it's definitely something for you to consider if you need a clamp meter. I hope you enjoyed the video. If you liked the video, please remember to give it a big thumbs up, and remember to subscribe to the channel for more videos like this in the future. I will catch up with you next time.